Okay, hello.
Hey,
All right,
friends.
let's start. If a spherical shell completely surrounds a bar magnet, what is the magnetic flux through the shell? Well, maybe one of the first things I should do is draw the magnetic field lines from a bar magnet. Bar magnet looks like this, north on the top, south on the bottom. Oh, I should change markers so it's easier to see. Now, magnetic field lines work a lot like electric field lines, okay? Electric field lines go from positive to negative. Magnetic field lines go from north to south, okay? Just like electric field lines, they never, ever, 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 ever cross, okay? And they can bend around to do funny stuff. So my magnetic field line should look something like that. And I get the apple of magnetism. Okay? So those are my magnetic field lines. Anybody have any questions about that so far? Okay, so let's surround it with a spherical shell. Let's put it real close so it cuts some of these field lines nice. Okay, so make it a little bolder here. So that bold line there is my spherical shell. So, what do you think the flux through that shell is?
The section between the magnetic field lines and the cell.
What is it? What? Remember, magnetic flux.
The cross section.
Magnetic flux
amount of
is
stuff that goes through stuff.
Yeah. A times B times sine theta. Was it?
Cosine.
You're right. Cosine. One of those two. Cosine. I'll have to listen to Paul Hewitt next door. Okay. So what do you think the flux through there is? Any guesses?
0.
Boom. 0. 0. Why is it 0?
Because there's no A in E.
Well, no, there is an A. Okay.
It's 0.
Surface area of a sphere is like 4 pi r squared. There is a B as well, but watch this. On the north side, I've got magnetic field lines going out through the spherical shell, right?
Right.
But that same line comes back around and then goes in through south. So if I call out positive, in has to be negative. Okay? And you can see every single time I go out of this sphere, I go back in. Okay? So total magnetic flux is 0. Total magnetic flux is 0. Okay? As it turns out, this is always, 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 always true. Okay? For a closed surface, that means like a hollow anything with no holes, magnetic flux through it will always be 0. Okay? This, by the way, has a very important consequence. Magnetism in general has no monopoles. You ever heard that?
Like if you do bar magnet, then no, it wouldn't have a north and south.
Right. If I chop this bar magnet in half, what I get is north, south, north, south. Okay? And I can keep chopping it in half until I get to one atom. Okay? And its little spinning electron, that spinning electron will have a north side and a south side. Okay? There's no way I can chop that little spinning electron in half to get a north half and a south half. Okay? There are no magnetic monopoles. There's no such thing as a north charge and a south charge. Okay? Unlike electricity, there certainly are electric monopoles. Positives and negatives. Okay?
What would be the repercussions if you were to isolate a pole?
If you were to isolate a pole, theoretically, if you took a north pole and went to the Earth's north pole, you would go whoop. Like you could hold on to it and like float up, which would be fun.
That would be pretty awesome.
Huh?
That would be pretty awesome.
Yeah.
Let's do that.
Like if you had a magnetic field like this. Okay. We know that electric charges moving through magnetic fields feel a force, right? But if I had a magnetic monopole,
Okay.
a magnetic monopole,
It's a little straight.
a magnetic monopole would go in the direction of the magnetic field, just like a positive charge would go in the direction of the electric field. Yeah, scientists are really disappointed that there are no magnetic monopoles because it makes this beautiful symmetry between electric forces and magnetic forces. But unfortunately, none found so far. I won't say they don't exist, but I've never seen one. Anybody have any questions? All right, let's try the review question. A circular disc has a radius of 5 centimeters and has a normal vector pointing in the positive I direction. Okay, so here's our disc with its normal vector pointing in the I direction. Okay, what is the flux through the disc if the magnetic field can be expressed as 1, -3, 2? Okay, 1, -3, 2 would give you a magnetic field that's like this. 1, 2, 3, and then 2 out of the board, so it's pointing like that way. That's our magnetic field. Okay? So how do we do it? What is it? Not cross, but dot. Dot product. Okay? When we write A times B times cosine theta, right? The area vector times the magnetic field vector times the cosine theta, what we actually mean is A dotted with B. Okay? Just another way of writing the same thing. Alright? In this case, A dotted with B is a much, much better way to do this. Okay? When they give you, usually when they give you Cartesian coordinates, much better to do dot product. When they give you polar coordinates, much better to do this version with A, B, cosine theta, because it's easy to find that theta with polar coordinates. Okay? So A dotted with B, first thing I need is the A. Remember the area vector? Area vector is the area times the normal vector. Okay? We know the normal vector is just 1 I hat. Okay? So we need the area. How do I get the area of a disk? Pi r squared. So A is going to be pi times R is 5 centimeters, so 0.05 squared. Somebody let me know when. What
78.54.
78.54 e negative what?
This is
0.05.
oh wait, my bad.
I got 0.0078.
0.0078 square meters. So the area vector would look something like this. Area equals 0.007800. Right? Totally in the I direction, the X direction. Okay? Anybody remember how to do dot product with 2 vectors? It's easy.
That's just
Just
thinking
small.
about
Uh-huh. X times X plus Y times Y plus Z times Z. Okay? So if you look at A and B, we've got 0.007800 dotted with, what is it? 1, -3, 2. Okay? So 1 times this plus 3 times this plus 2 times this gives us 0.0078 as our flux. What are the units of flux? Magnetic flux, I should say.
Chin.
Chin units.
Stomach.
Mega chins.
Beach ones.
Huh?
Beach ones.
0.5. Linos. Okay, let's see. Let's look at our units. Area is square meters. Oh wait, here. area is square meters. B is Tesla, so it's Tesla square meters. Yeah, trademark square. Okay, anybody have any questions? Okay. So today we were going to do a lab, but we have so many people out.
Let's go ahead and do it anyway.
Well, I don't have the stuff for it. I don't even have a lab sheet for it. What? I don't have internet at all. Still, yeah. That's why I'm taking roll on my incredibly advanced system. Anyway, clickety click. Yeah, I'll have to go home to upload these. So you'll be seeing these around 5, 6 o'clock. They take like hours to upload, because that records in like HD, and so the files are like a couple gigabytes each.
What?
Yeah. Luckily, when I upload it to YouTube, they have settings already built in. Huh? Yeah. Yeah, just look up. Yeah, go to the Springs Physics website. It's got the links on there, or just look up William Yarberry on YouTube. There are 2 channels. One's old, doesn't have any videos. The other is new and has 3 so far. What? What?
Like a lot of cat videos.
Okay, so today we're talking about big deal stuff, and it's all buried under my camera.
A big deal.
Oh well. Today we're talking about electromagnetic induction. Electromagnetic induction.
Let me get my.
Like something we should save.
This is extremely important. This enables modern society. This is how all the lights are on. This is how my laptop's running, although not so well. This is how the phone's running right there. Or at least how it's charged. I don't know how it's running right now. Okay, all electricity that we use, pretty much, almost all, is going to come from electromagnetic induction.
So we be.
Huh? Yeah, it's important. So what causes magnetic fields? Right, moving charge. Magnetic fields caused by moving charge. So what do you think happens if you have a conductor? There's a magnetic field through that conductor, and the magnetic field is changing. What do you think is going to happen? Okay, I've got a conductor, and I have a changing magnetic field. What do you think it'll do? Huh? Well, yeah, I have a changing magnetic field. So what does that make happen? Remember, most things in physics are reversible. Most things in physics are reversible, except for all thermodynamic processes.
You can go back and forth between
Almost. Look at this. If magnetic fields are caused by moving charge, what makes charges move? Changing magnetic fields, which will cause an EMF. Okay? So if I have a changing magnetic field, changing. Okay, if I have a changing magnetic field, that will cause charge to move. Okay? Now, it's not quite enough to say changing magnetic field, because like we showed before, if I've got some sort of surface lying parallel to this magnetic field, it doesn't really see the magnetic field. Does that make sense?
Mm-hmm.
It doesn't realize there's a magnetic field there because all the magnetic field lines are going parallel to it. Okay? So it's not so much magnetic field as magnetic what? Flux. Flux. Okay? Changing magnetic flux is actually what causes moving charge. Okay? And we have a lovely little rule to express how much moving charge we get. Okay? Called Faraday's law. You guys know Faraday? He came up with this. Huh? Sort of. The farad, unit for capacitance, is named after him. Okay? So this is Faraday's law. Okay, and Faraday's law says electromotive force equals the change in flux, the change in magnetic flux, I should say flux magnetic like that, over the change in time. The change in magnetic flux over the change in time. Big deal. Big deal. Huge deal. Biggest of deals. Okay? Now, one thing you might notice, magnetic flux tends to be small. Okay? Magnetic flux tends to be very small because magnetic fields themselves tend to be small. And areas tend to be small. For example, let's say I got a 1 meter loop of wire. Okay? So, or 1 square meter. 1 square meter loop of wire. Okay? Now the Earth's magnetic field is around 25 Gauss, right? 25 Gauss, which is, or is it 250 Gauss? Or is it 2.5 Gauss? It's like 25 e negative 5 Tesla. I'm pretty sure that's right. Okay? So let's say I've got this loop of wire out in space where there's no magnetic field, and then I bring it down to Earth in 1 second.
Holy crap.
It's gonna be like a huge.
Is it? Is it?
Is it?
Think about it. Flux is area times magnetic field, so it's 1 times 25 e negative 5. 25 e negative 5. Okay? Out in space, there's nothing, right? So we're going from 0 to this in 1 second. So divide by 1 second. Is that a big EMF? 25 e negative 5? That's tiny. That's tiny, 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 tiny voltage. You couldn't even feel that on your tongue.
Then why do you think it's that voltage?
Huh? Okay, so how is modern society possible if bringing a square hoop, or a 1 meter squared hoop, which is actually kind of big, it's like that big or so. Yeah, if that much, bringing it from space to Earth, because Earth has a pretty decently sized magnetic field, gives us that tiny, tiny EMF. Here's what they do. They do loops. Loops of wire. Lots and 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 lots of loops. Thousands, tens of thousands of loops of wire. Okay?
Everywhere.
What?
Loops.
Loops everywhere. Okay? So, if I double the number of loops, what do you think happens to the amount of flux? It doubles as well. And if I triple it, flux is going to triple, and so on and so forth until I have thousands and thousands of loops. Okay? So one little addition I can make to Faraday's law is N. N, where N is the number of loops. Okay? N is the number of loops. All right? One thing I should say real quick, loops, these have to be closed loops. That might be a little obvious. They have to be closed loops in order for current to flow. Okay? You want to try a quick example?
Sure.
Try a quick example and then probably shut that video off because it's probably running like 20 minutes now. 20, 30, something like that. Don't want them to run too long, otherwise it'll take days to upload. Okay. Oh man, I'm gonna be in Austin too. Okay, so let's say I've got a tiny, tiny magnetic field and a square loop of wire. How big should our square loop of wire be?
4.
4? Yeah, sure. 4 meters squared. That's a big loop of wire. 4 square meters. In a uniform magnetic field, we'll start it off at 1 Tesla. Okay, we'll be easy. We'll start off easy. Okay, and it's just one loop of wire. All right. My question is, what voltage will be induced in the wire? What voltage will be induced in the wire if I increase the magnetic field to, I don't know, what's another good number? 5? 5 Tesla in how long?
10 seconds.
10 seconds. Okay? Easy stuff, right? Remember, anytime I have a change in, I can rewrite that as final minus initial. Okay? So EMF is going to be number of loops times flux final minus flux initial over the change in time. Okay? So, let's see. Number of loops was just 1. Now, flux, remember, is magnetic field times area times cosine of the angle between them. Here we'll just assume they're perpendicular. So, blah, 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 blah. I got B final, A final minus B initial, A initial, all over. Change in time we said was 10 seconds. Okay? Now, quick question. Does my area change? No, my area does not change. So area final and area initial are the same. Weep, weep. So we could factor those out if we wanted to. Okay? So I end up with 1 times, area we said was 4 square meters, 4 over 10 seconds. B final was 5 Tesla, minus B initial was 1 Tesla. Okay, so we got 4 times 4 over 10, 1.6 volts. Okay, so there will be a potential difference in this wire of 1.6 volts. Okay, and then depending on the components attached to that wire or the resistance of the wires itself, you'll get a certain amount of current. Okay?
Yeah, but 1 Tesla is mega huge.
What?
1 Tesla is really huge.
Yeah, 1 Tesla is gigantic, 5 Tesla is 5 times as gigantic. It is. Anybody have any questions?
So this is about as simple as it gets.
Yeah.
What's more complicated?
We're going to start, instead of changing the area, we're going to start changing the angle. We can change the area as well. And then we need to determine the direction of the current. Because we know there's going to be a current, right? We have a voltage, there's going to be a current. We need something called Lenz's law. I'm pretty sure it's Lenz's law. L-E-N-Z. I'm pretty sure it's Lenz's law to determine, to determine the direction of the current. Magnetic flux does not like to change. It gets angry when you change it, and it makes a current to try and keep the flux the same. So that's what we'll look at next week on the next episode of AP Physics B. Okay, I'm going to stop the video and we'll do some homework problems or something. Say bye, everybody. Now you're on YouTube forever. Do something obscene. I'm kidding.